Well, so we're here at lecture 2 now, fundamental analysis. What are we going to do today? Well, I'm going to review a little bit about what we did in lecture 1 with the square root of 2. Talk a little bit more about the completeness axiom. What exactly does it say? We won't use it for any proofs, but I will sort of hint at use in a proof. We'll consider more counterintuitive examples. I think I'll skip this mean value theorem section today. Again, I'd highly recommend looking through this. Okay, you don't have to know it all right away, but looking through that to see the applications of the mean value theorem and to see sort of the deconstruction of its proof in terms of more basic principles. It's going to make more sense to you, though, overall, once we get to chapter 4. We will talk a little algebra, fields, not nearly as much as algebraic structures, though. Just a little bit of algebra. Ordered sets, ordered fields. We'll do this proof right here. Talk about why the rational numbers are defective for calculus. Actually, that's going to come in with the completeness axiom. And we'll talk about absolute value, norms, and something called the triangle inequality. All right, so what did we do last time? We did a proof that the square root of 2 is irrational. I did want to look a little bit at the structure of the argument here. So you can zoom in on the screen here. It was an argument by contradiction. Try to remember what we did last time. I'm not going to write it on the board this time. I'm just going to say it verbally. Well, I probably should say the statement, the if-then statement at least. So I wrote it as if x squared equals 2, then x is not an element of the set of rational numbers denoted by q. So in this structure here, if-then, the p is the clause that x squared equals 2, and the q, not that q, but the q up there, P implies Q. The Q that you're trying to prove is x is not rational. X is not an element of the rational numbers. The argument by contradiction structure is if you can prove that assuming P is true and not Q is true implies that two opposite things are both true. This wedge here means and. Those two things together, if this implies that is true, will imply the truth of Q. Okay, that's pretty abstract, okay? Think about it in terms of this example. The P clause is the statement that x squared equals 2. The Q clause, not the Q set of rational numbers, but the Q clause up there is that x is not an element of the rational numbers. Its opposite, not Q, would be x is an element of the rational numbers. So in constructing the argument, you assume x squared equals 2, and you assume, to the contrary, that x is rational. We want to show that that implies some statement and its opposite are both true, are and not are. But that can't happen. That's a contradiction. A statement and its opposite can't both be true. So if we can do that, the entire thing that we've done would then imply that Q, the clause Q, that x is not rational, is true. How did we do that? Again, I'm just going to say it verbally. We assumed x was little p divided by little q. Too many p's and q's here. Little p divided by little q. I could have used m and n. Little p and little q were integers. We assumed the fraction was reduced without loss of generality so that it neither, P and Q can't both be even. At least one of them's got to be odd. And that was actually the key because ultimately R is that one or the other has to be odd, but the not R we found was that they actually were both even. That was the algebra. Those watching the video, go back to lecture 1. I think it was near the end of class, right? Somewhat near the end of class to see that we could, certainly without loss of generality, assume the integers in that ratio, at least one of them was odd. They can't both be even because we assumed we reduced it. That was the R statement. The not R statement was that we found that they actually were both even. That's a contradiction. So the entire fact that we prove that this implies that, that whole thing implies that now Q is true, that in other words, that X is not rational. Are you going to have to do this kind of thing all the time? No, okay? You're not going to have to do this kind of logic stuff from discrete math all the time. I think it is good to think about once in a while. Okay? But you definitely won't have to do it. You won't have to do any truth tables if you want. Did you do truth tables in discrete math? Yeah. Okay. This manipulate allows us to see the digits of square root of 2. The first 10,000 as we zoom over here. There's 10,000 digits of the square root of 2. You know from the past that irrational numbers have decimal expansions that do not have a repeating pattern, and in fact pretty much no pattern at all for square root of 2. Irrational numbers can have patterns to the decimal expansions, just not repeating patterns. There's a decimal expansion with a pattern, but it's not a repeating pattern. That actually represents an irrational number. A harder question is, how do you know square root 2 exists? If its decimal expansion goes on forever without a repeating pattern, and in fact pretty much no pattern at all as far as we can tell, how do you know there is an infinite decimal expansion whose square root is 2? Decimal expansions are not really good enough to prove square root of 2 exists. So how will we do that? We actually will do that. We'll prove square root of 2 exists in here. Though we are doing it axiomatically, we're assuming the real numbers form a field, an ordered field, in fact, that satisfies the completeness axiom, which I'm about to show you. We could prove the completeness axiom if we went to more basic principles. We're not doing that because that might take a month or two. We want to start by assuming it because it's going to get us to where we want to go as fast as possible. So we're taking this statement here as an axiom. Though if we started with more basic principles, we could prove it. Not too many people are very interested in that kind of thing. But, okay. It's worth doing. I'm glad somebody did it and can learn about it. I learned about it. But it's probably not very interesting to most people. So we're taking this as an axiom. Every nonempty set of real numbers that is bounded above has a real number supremum. I haven't said what supremum means yet. Supremum is a synonym for what can be better described as a least upper bound. I did briefly describe it in lecture 1. Imagine a set on the number line. It could be an interval. Could be a set of finitely many points. It could be the set of all numbers of the form 1 over n, where n is a positive integer. There's lots of different sets you can create on the number line. Imagine that it's bounded above. Okay, I'm not going to write a definition of bounded above yet, but it should seem pretty intuitive. That bounded above means the set can't go off to infinity to the right. There's got to be some number that's bigger than all the numbers in the set. That would be a set that's bounded above. Saying it has a supremum means it has a least upper bound. It has an upper bound that is as small as possible. What would that mean? An upper bound that's as small as possible means any number less than that upper bound, which is as small as possible, would not be an upper bound of the set. That's what it would mean. It's okay that I'm not drawing on the board here? Can you visualize with me? Number line. It's got an upper bound for the set that we're considering. There's a number that's bigger than every number in the set. It's got a least upper bound. There's some upper bound that's as small as possible. Any number less than that least upper bound will not be an upper bound of the set.
What if you had an open interval though, like from 0 to 1, not including 1?
Not
How would
including
you
1?
find that upper bound?
So here's the notation we usually use for the open interval from 0 to 1. That is a set that's bounded above. It's got an upper bound, for example, 2, 3, 4. Those are all upper bounds. What would the least upper bound be? This completeness axiom says one exists. What would it be here for this example? 1.1, 1.01, 1.0001, or something else? Anybody feel confident? It's the number 1, actually. The number 1 is the least upper bound of the set. It is bigger than every number in the set. And any number smaller than the number 1.99999, don't make it a repeating nines, because that equals 1, truncated somewhere. That's not an upper bound. Because I could add on another 9, and that would be in the set. 1 is the least upper bound. It is the suprema.
How could that exist when 1's not actually in the set, though?
Good question. Sometimes the supremum's in the set, sometimes it's not. It is an upper bound of the set. Every number in that set is less than or equal to 1. And it is the least upper bound. Any number smaller than it, like 0.99999, stop somewhere, is not an upper bound of the set. I will write down definitions here. Next time I'll write down these definitions. But wait a minute. The completeness axiom distinguishes the rationals from the reals. I don't know if I've said that better. But all rational numbers are real numbers. Wouldn't every non-empty set of rational numbers also have the least upper bound? Since rational numbers are real numbers? The answer is yes and no. Yes, they have a supremum because they are real numbers, but that supremum is not necessarily rational, and that's the crux of the matter. As we will see. You might wonder why not ever state that every non-empty set of real numbers that is bounded below has a greatest lower bound, or infimum. Or is it infimum? Actually, I can't remember the way my grad school professors pronounced it. I think I usually just say inf, because that's what they usually said. Supremums are usually called sups. And infimums, I think it's pronounced infimum. Or infimums. Mostly people just say inf. So that's why I don't remember what they pronounced it as, because they always just said inf. Okay. I think it's infimum. I should look it up. I should have looked that up before class. An inf is a greatest lower bound of a set that's bounded below. Shouldn't we also say that that's true? We could, but we don't have to. That's the point. You actually can prove that fact from the other one. Essentially take all the sets, all the elements of your set, and negate them to create a new set. If it's bounded, if the original set is bounded below, the new set will be bounded above. It will have a supremum, a least upper bound, and you can negate that to get the inf of the original set. Tracking with me here? I know it's early. It's early in the morning, by the way, people who are watching this. It's really early in the morning, so we're doing our best to stay awake. I have my coffee. Oftentimes I have water, but I need coffee for this class. Later on, we're going to see that the completeness axiom is equivalent to something called the Cauchy convergence criterion. Every Cauchy sequence of real numbers converges to a real number. I'm not going to get into what that means at all. By the way, do say Cauchy here. Don't say Cauchy. Cauchy. Cauchy really hurts my ears. It makes me want to scream. Cauchy. Okay. Have you heard of Cauchy before? We did look at some counterintuitive examples last time. Let's look at more counterintuitive examples. Again, in real analysis, it is real important to come across, some people call them pathological examples. I'm serious, they call them pathological examples. Okay, because they're just weird, and people didn't quite even believe them at first. You can create functions that are continuous everywhere, but differentiable nowhere. Now, we're not going to talk about continuity until chapter 3. We're not going to talk about derivatives rigorously until chapter 4, with the mean value theorem. So again, we're thinking intuitively here. You can create a function whose graph can be drawn, so to speak, without picking up your pencil. But it's differentiable nowhere. It doesn't have a derivative anywhere. Somehow it's jagged everywhere. I'm about to show you such a function. Is it possible to visualize? Okay. It is possible, sort of. But you got to visualize it in the right way. Now, when I was in your place, when I was first taking real analysis and I was told this, the professor didn't try to draw it on the board, okay? So I'm sitting there trying to imagine what it looks like. And I'm thinking, okay, continuous everywhere, but jagged everywhere as well. How can that happen? The points on the graph, are they like atoms and they just keep going up and down? And the answer is no, don't think of it that way. Points are not atoms in math, okay? They're way, way, way smaller than atoms. Atoms, you know, they have some volume. Points are points. They have no volume, no area, whatever. They're idealized objects. We pretend we know what they are. Really? Okay, don't worry about it. Don't think of it that way. So how should you think of it? Don't worry about how I created this code here. There's an interesting function. If you take this function that's graph looks like this, and actually you imagine the graph goes on forever in both directions, it's periodic. And you call it function g of x, and you create this function here. It's an infinite sum involving g of x. It turns out this is a function that's continuous everywhere and differentiable nowhere. Although we can only approximate it on Mathematica. So even though you see the summation sign here going to infinity, here I'm letting it go to n, and we're only going to approximate it. What does its graph look like? We're going to see successive approximations. There's the first approximation, not a very good one. Here's the second one. Oh, I paused. I didn't know. Give it away too soon. There's the first approximation, or the 0th approximation. Here's the next one, the next one, the next one, the next one. These are all approximations of this continuous everywhere differentiable nowhere function. There we go. So I guess it's sort of possible to draw that to some degree. But is that really what the graph looks like? Well, sort of. On this scale, you might say. The key thing really is to realize that it's going to look basically the same, jagged, no matter what your scale is. And what we're going to do is we're going to zoom in near that red dot there. It takes a little while to render these pictures. Zooming in with the camera, it's a little hard to see maybe sometimes. If I move this slider, I'm really zooming in near the red dot. Now you see the graph changing in ways that should seem like it shouldn't change. That's because Mathematica is having trouble approximating it. If you stop at any point, it works for a few seconds to try to approximate it better. There's a better approximation. And basically, the point here is, no matter how far you zoom in, it still looks jagged. That's the best way to imagine it. No matter how far you zoom in, I could keep zooming in closer and closer. It would still look jagged, no matter what. It's an example of a fractal. Heard of fractals before? Okay. It's an example of a fractal. The jaggedness is still there at all levels of magnification. And that's probably the best we can do as far as imagining it. Functions can be differentiable everywhere. They can be smooth. But the derivative doesn't have to be continuous. You can have a function that's got a derivative, the graph is smooth, but the derivative itself doesn't have to be continuous. Excuse me. Everywhere continuous. It's sort of typically usually continuous. Here's an example. F of x is x squared times sine of 1 over x. If x is non-zero and f of 0 is 0. We looked at this example last time. It was the blue one. Actually, it was a slightly modified version of it. It had a slope of 1/2 for the origin. F prime of 0 was 1/2. This one, the blue one, has a derivative equal to 0 at x equals 0. F prime of 0 is 0. The red graph is its derivative. Now that graph is seems continuous, but it is strange in the fact that it's oscillating so fast near 0, and in fact it's oscillating infinitely often on any little interval containing 0. And because of that, the limit of the red graph as x goes to 0 does not exist, although f prime of 0 does equal 0. So the red graph is continuous everywhere except 0. It exists everywhere. F prime of 0 is defined, and it is 0 for this example. That can be proved. And in fact, it's not too hard to prove. I'd encourage you to try it. But because the limit as x goes to 0 for the red graph does not exist, the red graph can't be continuous with 0. The red graph is the derivative of the blue graph. So again, you want to keep these strange examples in mind. The derivative doesn't even have to be bounded. If I change the x here to an x squared, I get a function that's differentiable everywhere. The derivative exists everywhere, and in fact here f prime of 0 is 0. But in fact, the graph of f prime is not even bounded. Got to enter this. That's better. So the orangish, yellowish graph, I guess that's a gold, isn't it? The goldish graph, the oscillations are actually getting bigger and bigger without bound, actually, as you approach 0. But actually, f prime of 0 is 0 still. Weird, okay? Weird things can happen. And I'm trying to make you aware of it. Do you need to know these weird things right now? Not really, but I think it's not a bad idea to introduce them, to start getting you thinking about the fact that weird things can happen, and you got to be careful. Here's another counterintuitive example. Do recursive sequences before? Discrete math, maybe linear algebra, maybe. I just want to diffq. Define a sequence recursively by letting x0 equal 0.1 and use this recursive formula. Pretty ordinary looking kind of thing. So what does that mean? So x0 is 0.1. x1, if x0 is 0.1, by that formula is going to be 4 times 0.1 minus 4 times 0.1 squared. 0.4 minus, what would it be, 0.04? Check my arithmetic here. 0.36, that would be x1. Plug that into the formula to find x2. I'm not going to do the arithmetic, but it would be 4 times 0.36 minus 4 times 0.36 squared. And keep going. Gives you a sequence. NestList in Mathematica, the one on the screen here, is a way to see those iterates. And here are the first 50 iterations. So x0 is 0.1, x1 is 0.36, I was right. Good. x2 is 0.9216. x3, probably we're dealing with approximations now, is about 0.289014. Interesting. Very ordinary looking formula produces weird behavior. The numbers go up, they go down, they go up, they go down. If they get real close to 0, they stay pretty close to 0 for a bit, but then go away. If they get close to 1, they jump back down real close to 0. Weird. So that's counterintuitive just because it's unexpected, I guess. This is right. It really does. Never gets bigger than 1 or less than 0, it seems. Here's a number line graph of this. This is one way to visualize a sequence. So there's x0, 0.1. Watch the numbers bounce around. I suppose it might have been nice if I made them actually hop, but bounce around all over the place. Although, if you let it go far enough, seemingly it seems to be filling in the entire interval from 0 to 1. Does it really fill in the entire interval from 0 to 1? No, it doesn't. It's definitely not going to equal every single number between 0 and 1. In fact, it can't ever be irrational because 0.1 is rational and the formula is a nice polynomial with rational coefficients. It can't ever equal an irrational number. Does it hit every rational number between 0 and 1? I don't think so. I guess not, though I don't know that I've seen the proof. But it does basically fill in the interval kind of densely. Actually, that's an official term. It gets arbitrarily close to every number in the interval. Give me a number in the interval like 1 over pi, square root of 2 over 2. You're going to be able to get really close to those numbers. In fact, if you go out far enough in the sequence, you can get arbitrarily close, as close as you like. I also noticed that there seem to be more numbers near 0 and 1 than there are in the middle. More of a statistical property there, or probability property. Before I look at a histogram of that, here's another way to graph. This has a time series, you might say. As the iterations keep going up, that's another way to graph it. Can we make a histogram showing where things are most dense? Yep, you can. And yes, the majority of the numbers are near 0 compared and 1 compared to near 5. If you look on equivalent size intervals. So you can even bring probability into play. But this is strange behavior. Is it understandable behavior? You can understand it, but we're not taking the time to do that right now. Okay, all this stuff really is necessary for real analysis education. I'm not doing stuff that's extraneous to this class. I think it's cool, but it's not extraneous. It's fundamental to be aware of these things and to maybe try to call on these examples for future problems in chapters 2, 3, 4, maybe chapter 6 and 7. They could be relevant for future problems. They are important to know about. Again, we're going to skip this section for today. Let's go on to something new now. Fields. Does anybody think they can describe a field in one sentence? Should have read about the properties of a field. But weren't there like 11 properties? That would be a real big run-on sentence, wouldn't it? Actually, if you use algebraic structures terminology, you can describe a field in one sentence. If you didn't take algebraic structures, it's okay. But for those of you who had algebraic structures, you can describe a field more succinctly as a commutative ring with unity in which every non-zero element is a unit, right? Obviously. What? Remember rings? Rings have two operations, addition, read my fingers here, addition and multiplication. Rings are abelian groups with respect to addition. What's abelian mean? Commutative, right? With respect to addition, x plus y equals y plus x for all x and y. Abelian group with respect to addition. 0 would be the additive identity. X plus 0 equals x for all x. There is a 0. There is an additive identity. Rings don't have to be commutative with respect to multiplication. You remember that? What's an example of a ring that's not commutative with respect to multiplication? Can you think of one? Matrices, matrix multiplication. Yeah. So if you want them to be commutative with respect to multiplication, you say they are commutative. It's a commutative ring. You don't say abelian ring. You say commutative ring. What's a unity? Multiplicative identity, like the number 1. Or with matrices, the identity matrix. Square matrices. Every nonzero is a unit. What does that mean?
Has an inverse.
Has a multiplicative inverse, yeah. X to the negative 1 power. Also in rings, the distributive property holds, even in more general rings. Every field is a ring, right? But not every ring is a field. Every fields are a smaller part of rings. All fields are rings. If you didn't have algebraic structures, it's okay. You don't need to know this for the test. But for those who have it, want to round out your education here to remind you of some things. You remember these fields? Those are probably the biggest nightmares, right? I remember they were my biggest nightmares when I took algebraic structures. Adjoining roots, field extensions. I thought that was the hardest part of algebraic structures. Guess what? We don't have to do that in real analysis. We just deal with Q and R, and in fact, even mostly just with R. Mostly just with one field, R. So I'm probably not going to talk much more about other fields and rings. I don't know if it'll come up again at all. You may be happy to know. Probably happy to know. But R is a field. All the properties that you want hold true. Commutativity, associativity, distributive property. They all work, okay? And you may assume they work for your homework. R is a field. Q is a field. And like what I said with this homework, you don't have to even write the elements of Q as fractions. You can just say, let X be a rational number. It is a fraction of the ratio of integers. But you don't have to say that. You don't have to write that. You can just use the field properties of Q if you need them. You can write it as a fraction if you want, but you don't have to. R is an ordered field. There's an ordering to the numbers on the number line. You can define orders on sets as well, not fields, but more generally for sets. I could just do a silly example. Create a set S consists of the 2 letters A and D. And I can define an order on that set by saying A is less than B. Done. That's a silly example, but it's an ordered set if I want to create it in such a way. In this section, it's not required that you look over this, but if you want to round out your mathematical education, you can. I get into what a relation is, and in particular, what it means to be an ordered set with respect to relations. Kind of abstract stuff there, kind of like in the preliminaries handout. You won't really need to know that though. If you're interested, you can look into it. And here's my description of an ordered field in terms of the idea of it ordering as a relation. You don't really need to know what I have written here in the way that I have written it, but let's look at the way the book writes it. They write it in a more down-to-earth kind of way. Page 8. An ordered field is a field that's got an order on it that satisfies some additional properties, such as if x and y are both bigger than 0, That implies that x times y is bigger than 0, and it also implies that x plus y is bigger than 0. X is less than y, or y is greater than x, if and only if y minus x is greater than 0, or you could say 0 is less than y minus x. And by the way, y minus x is just our notation for really y plus the additive inverse of x. Right, with rings, technically speaking, initially you don't have the subtraction operation, but you can define it. Y minus x is defined to be y plus the additive inverse of x. We'll just write y minus x. Right, looking at the top, page 8 with me? Good to have your book with you to look at it. Ordered fields are fields with an order defined on them with these additional properties. And actually, according to the book, I didn't check this, property 3 can actually prove property 1. So it's a little redundant, but that's probably okay for clarity's sake. You can use those properties anytime you need them. Where might we need them? Well, maybe a problem like this. Let's do this example. Let's prove this. Go ahead and stretch. Yeah, yawning's okay. Don't do it too loud though. Try to keep your yawns discreet. No math pun intended. Let's try to prove what we see there. That's not an assumption. That's not part of the definition of an ordered field here. It's something we can prove based on the definition of an ordered field. If x is less than y and z is positive, then x times z is less than y times z. Multiplying an inequality on both sides by a positive number does not change the direction of the inequality. It's not stated as part of the definition, so it must be a property we need to prove. I'm not going to rewrite it on the board, but let's write the proof. And let's go ahead and do it in sentences here. Since x is less than y, it follows that y minus x is bigger than 0. Or 0 is less than y minus x if you prefer staying with the less than sign. Okay. What do we want to show? Well, we also know z is positive. We want to show x times z is less than y times z, or equivalently, subtract xz from both sides, yz minus xz is positive. Now you could write that in your next sentence as something like, we must show yz minus xz is bigger than 0. And I think that's helpful when you're first doing proofs like this. It's not necessary to write that kind of sentence, though it might be helpful. I'm not going to do it here to make my proof as short as possible. A little bit more elegant, perhaps, if you don't put we must show in there. Making things more elegant does sometimes make things more confusing for the reader when they're first trying to learn something. So elegance isn't ideal in math, and you should strive for it, though I will say it does typically make things more confusing for the reader. If you add phrases like we must show, that helps you, that does help the reader. It is okay to include.
So in our instance, our reader doesn't need it, will we get counted?
You kind of assume your reader is a mathematician who doesn't need it, yeah.
Okay.
That they know what you're doing here. And this is going to be a simple enough proof that they could, a mathematician would look at this property and the proof I'm about to write down, and they can think of it in about 1 second. Okay? It's experience. It's not, yeah, it's just experience, they know. What should I write next? I'm going to write the the expression yz minus xz, should I write any words before it? I'm going to end up factoring out the z, which essentially is the distributive property. By the distributive property, yz minus xz, you can factor out the z. It's the same as y minus x in parentheses times z. In reality, if you didn't just find subtraction initially, it'd be better to write it as yz plus the additive inverse of the negative of xz is y plus the additive inverse of x times z, but that does say the same thing. Since y minus x is positive and z is positive, it follows that this product is positive. That is part of the definition of an ordered field. I erased it up here. If x and y were positive, x times y was positive. Here we've got two positive things, y minus x and z. Their product must be positive. This must be positive. I'm just going to go ahead and say this is positive. Yz minus xz is positive. So xz is less than yz. Done. What do you do when you're done with the proof? Either put a little box, or a filled in box, or a slash slash, or a QED. You see those? They're too low. Okay. QED. You get excited. You start talking Latin. Quad erat demonstrandum, I think. Which means I demonstrated what I wanted to do. I did what I wanted to do. Or to a believer, PTL. Praise the Lord. Not necessary for credit, but fun to do, right? You got all these little quirky things you can do for fun. You gotta humor yourself in some way, right? With your homework for today, one picky thing that I'm going to look for, which you may not have thought of when you did the proof, you have these two rational numbers. You want to show there's a rational number in between them. Pick their average, essentially. You need to prove the average is between them. So you really did need to use properties of orderings. Why are the rational numbers defective for calculus? We're on the home stretch here. Hang on. Why are they defective for calculus? I already mentioned it because there are sets of rational numbers that while they do have a supremum that is a real number, it's not necessarily rational. It could be irrational, not rational. You don't have to write all this down, but you probably knew this fact already, actually, but stated in a different way. The fact that irrational numbers have decimal expansions that do not have repeating patterns implicitly means there are sets of rational numbers whose supremum is not rational. For example, the set consisting of decimal approximations to pi. Keep going forever. I did do it right? I only remember up to 3.14159. I don't remember anymore. Is that terrible for a mathematician to say? I've never taken the time to remember anymore. Okay, I just don't care. I might think I should care, but there's just many more interesting things to do in math. that set is a set of rational numbers. Those are all finite decimal expansions, truncated. A bunch of zeros after them. But the supremum of this set is pi, which is not rational. By the way, the proof that pi is not rational is much, much harder than the proof that square root of 2 is not rational. Square root of 2 was proved not rational 2,300 years ago. Pi was proved not rational, I'm guessing, maybe 250 years ago, 1700s, I think. I think that was about the time E was proved not rational as well, I'm guessing. Are there any patterns to the digits of pi? You can make a histogram of the digits. Well, there's the first digit, 3. 3.0. Okay, here we go. Now we got to separate it into digits. What? No zeros? Okay. I guess this bar represents zeros. 1s, 2s, 3s, 4s, 5s, 6s, 7s, 8s, and 9s. In the first 5,482 digits, I think, including the 3 in front, there are about 500 zeros, about 580 ones, 542s or so for pi. And you keep going, and these bars change in relative heights. Is there a pattern to this? Probably not in the long run, maybe in the short run. In the short run, you can say there are lots of 1s and 9s here. There's like 5s. But in the long run, there's probably no pattern. Do the same thing for E and square root of 2 here. There's a more extended form of that set that I wrote on the board there. Not the entire set, right? That goes on forever. So, because there are sets of rational numbers whose supremum, if it's a bounded above set, is an irrational number, not rational, that does mean that rationals are defective for calculus because limits of sequences of rational numbers don't have to be rational, so that your theory of limits is not complete without irrationals. That's why they're defective. Do they really exist? Well, we do have to prove square root of 2 is, we already proved square root of 2 is irrational if it exists, but we do have to prove it exists. So. Seems funny. We do still have to prove there is a number whose square is 2. Let me give you a hint at how we're going to do that, which we'll probably do next class period. I think we'll get to it. We'll see. Consider this set, the set of all real numbers, and we are assuming the real numbers exist, such that in real analysis we typically tend to put colons for such that's in these set builder notations instead of vertical lines, because we want to reserve vertical lines for absolute value. You remember in algebraic they use colons or vertical lines? Lines? Okay, yeah. Algebraists tend to use vertical lines, analysts tend to use colons. Such that x squared is less than 2. Turns out that set is bounded above. Claim its supremum, which would exist by the completeness axiom, is the square root of 2. Sup s, the supremum of s is what that means. Least upper bound as small as possible. No number smaller than the least upper bound is an upper bound of the set. Claim that number squared is 2, exactly. So it exists by the completeness axiom. We're essentially assuming it to exist, the supremum. But we still have to show that its square is 2. And that's not real easy to do, but it's doable with enough effort. By me, I can probably figure it out within 15 or 20 minutes if I'm doing it from scratch. If you were doing it from scratch without ever seeing an example, like it, I don't know, could take between anywhere between an hour and a month. Or maybe not at all, but with seeing some examples, then hopefully you would improve. Let's finish the class off by looking at the triangle inequality. I do have some other stuff here. By the way, these last sections that say extensions, I do have interesting things in those sections. For example, this one's called weird formulas involving pi. I wonder what that summation is. Pi squared over 6. What? Pi? Where are the circles? The sum of 1 over k squared, in other words, 1 plus 1/4 plus 1/9 plus 1/16 plus 1/25 plus 1/36, etc. forever, that infinite sum equals pi squared over 6. Why? That's amazing. That's astonishing. What about this one? Pi to the 4th over 90? What? Pi to the 6th over 945? They all involve pi. Those are all even powers in the denominator, though. What about an odd power? Zeta of 3. Not such a simple relationship to pi. Not worth describing in terms of pi at all. What is zeta? It's called the Riemann zeta function. I'll talk more about that later. What's the triangle inequality? Let me just state it and then we'll end class. For all real numbers x and y, you can write the following inequality. The absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y. Where are the triangles? Well, there's a triangle. And there's almost a triangle. No. That's a for all. That's a less than or equal to. If you interpret x and y as vectors, something similar is true for their lengths. And intuitively, it's because the length of one side of a triangle is less than or equal to the sum of the lengths of the other two sides. The shortest distance between any 2 points is along the straight line between them. Let me just say that this is super duper useful. You will use it on, I don't know, should I hazard a guess? 25 to 50% of all your homework problems. As a guess that I'm not sure about the accuracy of. And you use the triangle inequality. At first, I do want you to say by the triangle inequality. But then after some point, that just gets too silly. And you just, it's true. You can say, shorthand, you can say by the triangle inequality. There's a shorthand for triangle inequality. That's a triangle, not a delta. It's not the delta inequality. Just as a shorthand for the words triangle inequality. All right. We're ending today here at 55 minutes. I still have to put grades up on the